Yeah, I think we can maybe start if it's okay with you, Steffi. Yeah. So hello to everyone. So we are very happy today to host Steffi Tofelde, who is a former member of Landscape Live, which was very involved into Landscape Live. So it's very nice to have you here, Steffi. So Steffi is a postdoc at the University of Potsdam in the geological remote sensing group. She will talk today about what sets the width of valley floors. And we will share this seminar together with Aditi, Dave, and it's not Rebecca who is sharing with us. No, it's Rebecca? No, it's Michael. I don't remember. Or Rebecca and Michael. So Steffi is going to present during a few tenths of minutes. And the chat will be disabled during the seminar, and we will open the chat for questions close to the end of the seminar. And during the question, you can also, if you want, raise your hand to ask for the mic if you want to directly ask some questions. Okay, I think I've said everything, and the talk is recorded. So if you do not agree with that, you can still leave the room. But Steffi, I think the floor is yours. Thank you very much.
Yeah, thank you, Philippe, for the nice introduction and also for the invitation to now speak here at Landscapes Live. So what I have done for today is preparing a talk, as Philippe has already mentioned, that is organized around the question, what sets the width of valley floors? And in order for everybody to warm up for this topic, I actually start by showing you a handful of photos. And these photos will all show mainly fluvially carved valleys. And I would like you to focus in particular on the differences in the cross-sectional shape. So the first example we can see here is the Muraca River in Montenegro. Then the second example is the Ala Acha River, or it's a river in the Ala Acha National Park in Kyrgyzstan. We have a tributary to the Narin River, also in Kyrgyzstan. And then we jump, quite a big jump to South America. This is the Rio Toro in Argentina. And then we actually jump back to Kyrgyzstan, and this is now the Narin River itself. And when we now compare these 5 different sites, we can see that although they are all fluvially carved valleys, they vary quite a bit in their cross-sectional shape. So especially when we compare the width of the valley bottom to the height of the valley. So in general, in the long term, we can think about the height or the depth of the valley as being the result of vertical river incision. And the width of the valley floor is the result of lateral river erosion. But in general, I would say in landscape evolution studies over the last decades, we have largely focused on vertical river incision. So we developed methods to quantify vertical incision rates. We looked at processes of incision, and we were looking at controls of river incision. And a lot less work has actually been done on lateral river erosion. So we understand a lot less about how valleys actually widen and what are the parameters that control the width of valley floors. So why is that a problem, or why is that actually important? So if we don't include lateral river erosion in landscape evolution models, it means that these models are actually not able to reproduce this broad range of cross-sectional valley shapes that we observe in nature and that we have seen in these different examples that I just showed you before. And that also means these models are not really able to predict how such valleys would evolve in the future, for example, if environmental conditions would change. And I did bring an example. This is a nice study from Abigail Langston and Greg Tucker, and they have particularly looked at the role of lateral erosion in landscape evolution models. So here on the left, you can see a model that was run in LandLab, and they have included a component for vertical river incision, but there was no lateral erosion included. And you can see down here, this is a cross section. So it's like the distance versus elevation that was extracted here along this red line. And we can see such a model, or such a landscape evolution model, would generate these like textbook-like V-shaped valleys that have a very narrow valley floor. So it's as wide as 1 pixel or as wide as the river. However, only when they started to implement a component for lateral river erosion, they actually managed to get valley floors that get a little bit wider, as you can see here or here. and that start to resemble a little bit more what we've seen in the previous examples. So I think what they have been doing here is a really good first attempt in that direction, but what we really need right now is actually field data to test this model and other models that have implemented some lateral erosion, just to see how well the equations that we actually use really work. And in general, we need to gain a better understanding of what controls actually lateral erosion, what controls valley widening, and what are the control parameters on valley floor width. So in order to do this, to address this question a little bit, I have subdivided my talk in kind of two parts. There's a first part where I will summarize a little bit on what we already know about valley floor evolution and the controls on valley floor width. And then in the second part, I will move to our new study that particularly addresses the role of lateral sediment supply on the width of valley floors. So I'm going to start by looking at several parameters that have been shown to play a role when it comes to the control of valley floor width. And this here's a study that was performed by May et al. And they have measured the width of valley floor in Harvey Creek. It's a little catchment in the Oregon Coast Range in the Western United States. And what they have observed is basically a typical pattern that has been observed in many other places as well. So they could see that the width of the valley floor scales with the upstream drainage area following this power law relationship. So that it's a straight line because the x is unlocked space. And oftentimes we would consider the drainage area as a proxy for water discharge. So what this shows is that in downstream directions, valleys or valley floors generally grow wider with increasing catchment area or increasing discharge. And I think what is also interesting for reference, they have put here the regression line for the equivalent relationship between the width of the channel and the drainage area. And we can see that the channel width increase in downstream direction has a slightly lower exponent in the power law relationship compared to the exponent of the valley width relationship. Okay, but discharge or drainage area is definitely not the only parameter that is important. A second parameter that probably plays a big role is lithology or material properties, rock strength or erodibility. So this is a study by Langston and Temmer from the French Alps. And what they have done is they measured valley width in 5 different bedrock valleys. But in addition to measuring the width, they have also identified the different bedrock lithologies. And they have grouped them in soft, intermediate, and hard lithologies, which are indicated here by the different colors. And then they did the same thing. They plotted valley width against the drainage area, but they performed the regression for each of the 3 groups separately. So the colors don't perfectly match, but blue is the soft lithology, green is the intermediate lithology, and red is the hard lithology. And we can see that the power law regression does vary between the lithologies. So if we take a look at a given drainage area or a given discharge, it looks like, despite a lot of scatter that is still in the data, valleys generally grow wider in softer lithologies compared to harder lithologies. Okay, so water discharge and lithology or rock properties probably play a role. A third parameter that most likely, or that probably plays a role, is uplift rate. So this is a study by Alex Whittaker and colleagues from the Rio Torto in the Apennines in Italy. And they have also measured valley floor of this little catchment that crosses normal fold here. And this normal fold can be seen also here in this figure on the right. So to the right here, this is downstream of the normal fold. Then we have the gorge upstream of the normal fold, and then this part high up in the catchment. So what they plot here is not just the valley width, but they actually plot the ratio of the width of the channel over the width of the valley. So it means like a ratio of 1 means the river is as wide as the channel, so it fills up the entire valley bottom. And these are generally narrower valleys, while when we have a very low ratio, it means the valley is a lot wider than the river that flows through it. And so we can see downstream of the normal fold, we have very low values, so the valley is extremely wide compared to the river. Upstream in the gorge, so where we have most of the uplift, the ratio gets closer to 1, so the valley becomes narrower, and then even further upstream, the ratio decreases again. So this study suggests at least that uplift rate might play a role, but in the end, it's only half of the story, because there is another story. Snyder et al., they have investigated the role of valley flow width at a very famous site for geomorphology, I guess, the Mendocino triple junction. So here, this is Cape Mendocino, and here, this is the San Andreas Fold. And this region is characterized by a quite strong latitudinal gradient in uplift rates. So what we can see here is a record of uplift rates versus the drainage basin numbers. So the numbers are organized going from north to south. And we can see we have a zone of high uplift of about 4 millimeters per year here at these catchments that are called Ode and Kinsey. So this is located here at this Kings Range region. But then in comparison, if we go down here to the catchments called Hardy and Juan, here the uplift rate is pretty low, so that it's about 0.5 millimeters per year. So what they did is they grouped the catchments in the low uplift rate zone and the high uplift rate zone, and then they also measured valley width against upstream drainage area. And it's maybe a bit hard to see, but the gray data points, they belong to the high uplift rate zone, and the black data points belong to the low uplift rate zone. So again, valley width against drainage area. And then when they performed the power law regressions, they could actually find no significant difference in the scaling relationship between width and drainage area for high and low uplift rate zones. So it seems like the role of uplift is not totally clear. Okay, and the last parameter I would like to mention that might be important is lateral sediment supply. And what you can see here is a photo from a field study by Luca Malatesta. And they have been suggesting in this study that the height of the wall plays an important role when it comes to the evolution of the valley. So what they were suggesting, it's shown here in this little cartoon. So if we have a river that sits at the valley bottom, and this river starts to move laterally, it actually starts to undercut the wall. And as a consequence, this wall will actually collapse, and all this sediment that collapses will form this talus pile at the wall toe. And we can nicely see this here actually in the field image. And this pile of sediment now actually protects the wall from any further erosion. So the river needs to remove all the sediment before it can actually attack the wall and widen the wall erode the wall and widen the valley any further. So the idea is the higher the wall is, the more sediment collapses for each step sidewards. So the longer it actually takes to remove it, and therefore this might reduce the widening rate. And in their particular example, they were even suggesting that if there is a lot of sediment that piles up here at the bottom, there is even the option that it actually narrows the valley floor, or that it, as a consequence, even the river is narrowing. So if we now have the same amount of water, but the valley floor is narrower, the river needs to get deeper. This increases the basal shear stress, and it actually can promote river incision. But also here, this is not totally clear, because there's also potentially some contrary effects of lateral sediment supply on the behavior of the river, as was proposed by the study from Charlie Shobi et al. So they show here a photograph from Boulder Creek. That's a river that drains the eastern flank of the Colorado Front Range. And what they were suggesting is that as the river incises, there's lots of blocks that sit here on these steep hill slopes, and they actually get delivered to the channel when these hill slopes oversteepen. And these big blocks, they then sit on the river bottom, basically, or on the riverbed, and they inhibit further river incision, which then might promote lateral erosion instead. So I think the role of sediment supply is very unclear. The amount of sediment might play a role, but maybe it's also actually the size of the sediment that does play an important role. So from those different field studies that I've shown, we have some ideas of different parameters that seem to scale with valley width. So they probably play some role when it comes to the controls of valley width. But it gets a bit harder if we want to study the evolution of valley width through time in the field because of the long time scales. But a nice way out are, for example, analog experiments. And this is an experiment from Aaron Buffe. So we are looking down at the experimental setup from above. And here, this is the upstream end where water and sediment get supplied. And here at the downstream end, the water and sediment can just fall off, basically. And what we see here is the end of the experiment, but what they started with is just a single straight channel, so a narrow valley in a way. And then they tracked with overhead images how this valley actually evolved through time. And this is shown here on the right. So this axis label of normalized cumulative fluvial area is basically a proxy for valley width. It describes how many pixels then for the first time have been covered by water. And this is plotted against the duration of the experiment. And all these bluish data points are the data points that were extracted from the overhead photos. And then in red, we have an exponential fit to these data points. And what this suggests, and other experiments have suggested this as well, is that the evolution of valley width through time can be described roughly by such an exponential curve. So I will now try to bring these different ideas a little bit together to come up with a very simple model of valley width evolution. So as we've just seen in this previous slide from the experiments, that if a valley is in a phase of widening, the evolution of the width through time can be roughly described by such an asymptotic curve. And the reason why this curve is asymptotic is because the actual valley widening rate decreases through time. It decreases with increasing valley width. And the reason why the widening rate decreases through time is, or it has been suggested by Hancock and Anderson in the early 2000s, that the reason for this is that with increasing valley width, the river actually spends less time at the walls to erode the walls. So you can imagine in a very narrow valley, a river that moves laterally touches the walls all the time. But if we have a very wide valley, the river spends most of its time somewhere in the valley floor and doesn't even erode the walls. So the valley widening rate actually decreases. So that means in a simple way, we can think about the width of a valley that we do measure at a certain time when we go out to the field, for example, is a combination of two things. It's a combination of the widening duration, so how far are we within this curve, and what is the widening rate at that specific site. And the widening rate, again, it changes through time. So this then brings up the next question: what actually sets the rate of lateral erosion in those times when the river does touch the wall? And I think the efficiency of a river to erode a valley wall, as we have seen before, depends on several different parameters. Most likely discharge plays a role. Probably the sediment that is carried by the water also plays a role, because we need the tools in the water to actually erode the wall. The lithology probably plays a role. Other people have suggested that the gradient of the channel might be important, or also the plan form curvature of the channel might be important. So all of these parameters I'm summarizing here as the so-called lateral transport capacity. And what this means is, given a certain set of boundary conditions like discharge, sediment carried in the water, plan form curvature, So given these boundary parameters, there's a certain amount of sediment that can be transported away laterally by the river from these walls. So that means in order to get the real wall retreat rate, which is called ER here, so the lateral transport capacity is the QL, but the real wall retreat rate then is scaled inversely with the wall height, because as we've seen before, for a high wall, we have more sediment that needs to be removed for a step sidewards. And for a low wall, there's less sediment that needs to be removed. So this simple model, we can also describe by an equation. And this equation down here basically says that the change of the width of the change of a valley width through time is simply the product of two things. It's the lateral erosion rate in times that the river touches the wall, times the probability that it actually does touch the wall and is not sitting somewhere far away from the wall. So the probability or the fraction of time that the river touches the wall can be described, as I said before, was suggested by Hancock and Anderson, by the ratio of the width of the channel itself to the width of the whole valley. And the erosion rate of the valley wall, the lateral erosion rate, is then the ratio of the total lateral transport capacity, so the total amount of sediment that can be removed laterally, divided by the height of the wall. Okay, so that was kind of a very brief summary of some of the ideas, what we have on valley flow evolution. And with these ideas in mind, I would like to move over to the second part of my talk, where I'm going to focus particularly on the role of lateral sediment supply on valley width. And I would like to start by actually coming back to this model to state an initial hypothesis. Because our idea was, if we now take this model and we take comparable durations of widening, so we compare different times along the x-axis basically. And if we also assume that the transport capacity is comparable and solve this equation, then this equation would actually predict that the width of valley floors should scale with the square root of 1 over the height of the valley wall. So that was the idea we wanted to test. And in order to test this, we were focusing on a very particular feature in landscapes, and these are paired alluvial river terraces. And I think paired river terraces are quite interesting for two reasons. First of all, paired terraces have the big advantage that they actually preserve information on valley width and also height of the according wall of the past, or for different points in time in the past. So we can see here, we can measure the width of the valley floor, and we can measure the height of the wall that needs to be actively eroded by the river when it touches the wall. But we can also reconstruct width from these paired terraces at different points back in time. The reason why we chose these alluvial terraces is because the material properties are rather similar, so we don't have to worry about changes in lithology so much. And the second reason why I think they're interesting is because it's not totally clear why they exist or how they form. And what I mean by this, I'm trying to explain in the next few slides. So this particular set of terrace sequence that we can see here, it's in the Rio Toro in Argentina. This is the site where I worked during my PhD. And here you can see a schematic cross-section of this terrace sequence. And during my PhD, I spent quite some time combining different dating techniques to actually reconstruct the terrace chronology. And I don't want to go into detail about the ages here, but the point I want to make is that what we figured out was, if we look at the evolution of river elevation through time, it looks like one terrace level has been formed roughly every 100,000 years. So we had phases of incision and aquadation roughly following the 100,000 year Milankovitch cycle, so the eccentricity cycle. And that's why we think this terrace sequence has been formed due to climate changes. But this particular terrace sequence is not the only one. It's not unique. There's paired alluvial terraces in many places around the world. And oftentimes they are attributed to cyclic climate changes. And this is because these terraces form because we have phases of river incision, but these phases are interrupted by phases of lateral planation or even aggradation. So in order to form an entire terrace sequence, we need to have repeated switches between incision and planation, incision, planation. And therefore, in order to get repeated cycles, these terraces are often attributed to cyclic climate changes. But climate changes alone cannot really explain why these terraces form. And the reason I try to show here. So this is a very simple sketch that actually shows the difference between the minimum requirements in order to form a classical V-shaped valley and a paired terrace sequence. So in order to form a classical V-shaped valley, there's only one net requirement, and that is that we have overall net river incision. When the river incises, it oversteepens the walls and the hill slopes will eventually respond to the new base level. However, when we try to form a terrace sequence, a paired terrace sequence, there's two requirements. So on the one hand, we also need to have net river incision, but these phases of incision, they need to be interrupted by phases of lateral planation or maybe even aggradation. And I think these alternating phases, they potentially can be explained by cyclic climate changes. For example, this can happen due to changes in water discharge or sediment supply. But then there's the second requirement, and this requirement is that with each step of incision, the valley needs to narrow. And I think this narrowing cannot so easily be explained by cyclic climate changes. So we were questioning ourselves, what is it actually that drives this narrowing at sites where we formed paired river terraces? And we were thinking about different potential explanations. So one way of how we can theoretically get a reduction in valley width through time is simply if we would reduce the widening duration. So if we would, in the first step, widen for 10,000 years, in the second step only for 5,000 years, and in the last step only for 1,000 years, we would get a reduction in valley width. The other option, if we think the widening duration does maybe not change so much for each phase, we could achieve a reduction in width if we increase the widening rate after each incision step. And that could potentially be done if we would, through time, decrease the total amount of water discharge, or maybe the amount of sediments that can act as tools in the river. So if we would reduce the lateral transport capacity through time. Or the other option would be that to increase the wall height with each step of incision. So if we think about these terraces in Toro again, and we actually compare them to a global climate record, so this is like the global benthic oxygen isotope record from the Quaternary. And if we look at the time span in which the terraces in Toro were formed, so roughly the last 500,000 years, then we can see, if we look at these climate cycles, there's no obvious reduction in the amplitude or the wavelength or the period of these climate cycles. And because of that, we think it's rather unlikely that this terrace sequence was formed due to a decrease in widening duration or due to a long-term decrease in water discharge or sediment supply. So we think that such a setup is actually a quite nice site to test this hypothesis of if the wall height potentially plays a role here. So in order to test this, we did not only pick this one site, we actually went through the literature and tried to compile alluvial terrace sequences all around the world that have been associated to Quaternary climate changes. And there's of course some requirements that we need to fulfill. So first, we only picked terrace sequences that most likely have been climatically formed. We only picked ones where high resolution cross sections have been available in the publication. So we did not extract the information from the 30-meter SRTM or so. We only pick cross sections that have been published based on field measurements, for example. And we only pick cross sections where there's a minimum of 3 terrace levels preserved, because we wanted, for each site, we wanted to have several measurements of width and height through time. So this ended up in 12 different data sets. And in all of these data sets, what we measured was the width that the valley floor had at different points in the past. And we also measured the according height of the terrace. So what was the height of the wall that needed to be eroded by the river when it moved laterally. What we also measured is the total valley height. So that means it's not only the height of the terrace that is adjacent to the river, but the height of all terraces above the river. So we could think of this as the cumulative terrace height, maybe. Okay, and with these data sets, we then tested our hypothesis. So remember, we wanted to test the scaling, whether the width of the valley floor scales with the square root of 1 over the height of the wall. And this is what you can see here. So you see the width of the valley floor against the height of the equivalent terrace. And the different colors are now representing the 12 different data sets. And then the lines are representing the regression based on this relationship here. So we can see, first of all, that in 10 out of 12 cases, we actually have a positive relationship. So with increasing valley width, we have higher terraces, or the other way around, with higher terraces, we have also wider valleys, which means this does not really work with our hypothesis. And then also, if we look at the R-square values, so for each of these regressions, we calculated the goodness of fit by calculating the R-square value. And down here, you see the distribution of these R-square values between 0 and 1. You can see that these R-square values are basically distributed all over the place between 0 and 0.8. So we have a median R-square value of 0.43. It's not really convincing regarding our initial hypothesis. But then we made a quite interesting observation. And what we observed is that at each of these 12 sites, the width of the valley floor shows very strong negative linear relationship with the total valley height. So it's not related to the height of the terrace that is actually directly eroded by the river. It seems to correlate very strongly with the height of all terraces that are above the river. So also here for this linear regression, we calculated the R-square values. And you can see down here, they are all above 0.9. With a median R-square of 0.97. So what this observation shows is that in order to form paired terraces, the valley does not even need to narrow with each incision step. It seems that this narrowing happens in a very systematic way. It looks like the reduction in valley width seems to scale linearly with the height of the valley, of the total valley. And again, it's not the height of the terrace, it's the height of the total valley. So it's not this height as we expected, it's the entire height that seems to play a role. So wall height somehow plays a role, but not exactly as we maybe expected. So when we saw this data, we thought there's basically 2 options now. My first idea was, by looking at the data, this is just a sampling bias, because I'm only looking at sites of paired terraces. By definition, I'm looking at sites where the valley is narrowing. So I'm not analyzing any sites where the valley width has stayed constant or increased. So maybe this is simply the result of how I actually pick my study sites. The other option is, if it's not a sampling bias, it might be a physical process or a physical parameter that does scale linearly with valley height and that is controlling valley width. So what we did is, in order to investigate the role of a potential sampling bias, we generated synthetic data sets, and we generated millions of terrace cross sections with different boundary conditions. And then we statistically compared the field data sets to our different synthetic data sets. And I don't have time here to show these comparison, but what comes out of it is that we actually think it's extremely unlikely that this is just a sampling bias. So if it's not a sampling bias, then the question is there a physical process or a physical explanation for this? So can we explain the width of valleys and why they actually scale with the height of terraces? So we have been thinking about this a lot, and we have tried to come up with lots of different explanations. And in the end, so far, we only came up with one explanation. So in order to explain this field observation, we derived a new model. And this new model is in a way very similar to the previous model that I have introduced to you in the beginning, but it has some specific differences. So it agrees with the previous model that the idea behind it is that the width to which a valley widens is basically the result of two opposing processes. On the one hand, we have the ability of the river to remove laterally supplied sediment and to drive further widening. And that is described here by this product of P and QL. So the lateral transport capacity of the river times the probability that the river is actually at the side of the valley. And on the other hand, we have the contrary process, and this is lateral sediment supply that comes in and that protects the wall from further widening. So that's the same idea that we had before. But now the difference is that in the previous idea, the lateral sediment supply, the QS, only came from direct erosion by the river. So if the river moves laterally, it undercuts the wall. This is the amount of sediment that gets generated and that needs to be removed. So it's the erosion rate by the river. And we now actually think there is a second source of sediment that was not taken into account before. And that is, we term this the river independent hill slope erosion. And that's called, that's the EH here. So the hill slopes erode, especially these upper ones here, even in times when the river can't control them anymore, when the river can't touch these walls anymore, but they still erode due to rainfall and gravity and so on. And this sediment also gets transported down to the valley. So that's the first difference. And then the second point is, in order, or we can only achieve a linear relationship for a very specific case. And this is for the very special case when these two opposite processes balance out each other. So in other words, when some lateral flux steady state between sediment input from the sides and sediment removal by the river is reached. So if we combine these model ideas with the idea of having like a lateral balance, and we solve these ideas for valley width, we actually come up with this little equation here. And as you can see, this equation describes how valley width scales negative linearly with the height of the total valley. So that's the nice thing. Our model was purely derived to actually explain the observations from our field data. And if the model is somehow true, then these different regression slopes that we see here, and they are the different regression slopes for the 12 different study sites. And these differences in regression slopes are due to local differences in hill slope erosion rates, local differences in lateral transport capacities, and W0 is a parameter that we call the unconstrained valley width. So it's the width to which the valley would theoretically evolve if there wouldn't be any lateral walls. So of course, this model has certain assumptions that come with it. And eventually it should also be tested against independent data. So the last few minutes of the talk, I would like to talk about these two things. What are the assumptions? And maybe some initial tests against independent data. So I think there's three really main assumptions that go into this model. And the first assumption is that it only works if sediment gets actually transported across the terrace surfaces to the modern floodplains. So if all the sediment that is eroded up here would just be trapped on this next terrace level, that wouldn't work. So the sediment needs to be transported all the way down to the modern river. The second assumption is that there's no drainage network forming on the terrace surfaces. So what we mean by this is that our model only describes the evolution of a cross-section, so that the lateral input of sediment needs to be more or less evenly distributed. So it must come in at many places and not just at a single tributary. And the third assumption that we have to make is that this hill slope erosion rate is roughly constant with height. And that's why we see the strong scaling between width and valley height. So I'm just going to show you some images, because oftentimes terrace surfaces are thought as traps of sediment, where sediment just gets stored and not transported any further. However, if we look at this is an image from the terrace sequence in the Rio Toro again. We can actually see that there are some, we could maybe call them transport slopes. They're very gentle. And if you stand on these terrace surfaces, they look extremely flat, but it looks like sediment might actually be transported across these flat surfaces down to the next level and eventually down into the modern valley floor. And it's the same site, just a photo from a different perspective. Regarding the overlapping lateral input, we can also see here that there seems to be sediment coming in from many points. They all overlap with each other. So the idea of a kind of even lateral input also seems to be okay. I have some Google Earth images from some of the other sites that we have analyzed, especially sites where there's no vegetation, so we can see the structures a little bit better. So this is the site from the study of Poisson and Awak in the Kuitun River in northwestern China. So the modern river is actually flowing down here. And these brownish surfaces are the terrace surfaces. And what we can see here is that there is some kind of network, some channelized structures that actually might transport sediment from these terrace rises across down to the next level and eventually down to the modern valley floor. And also here we can actually nicely see this overlapping lateral input. This is another image. This is the study site of Wang et al. At the Sutlej River in Tibet. So you can see the modern river flowing down here. And also here on these different terrace levels, we can see these channelized structures that actually might allow sediment transport across these very flat surfaces. So these are just a couple of examples, but I think regarding assumption 1 and 2, they might hold true. Regarding the third assumption, we really don't know. At least to my knowledge, there is no data set that exists that we could use to test this assumption at the moment. So what we would need is really quantifying wall erosion rates at different terrace elevations at a specific site. Okay, so this is about the assumptions, and then this brings me to this last bit. Ideally, we should test the model against independent data. So the good thing is that the parameters that describe the model are all parameters that we can quantify in the field, or at least estimate from parameters that we can quantify in the field. But also here, as far as we know, there's no data set at the moment or no site where all of these parameters have really been quantified. So all we can do right now is doing some very first order tests. So what we did as one of these first order tests is we returned to the data set that I have showed you in the very beginning. This was the data set from Langston and Temmer from the French Alps, where they had investigated valley width against drainage area for the different lithologies. But the nice thing is they have also quantified valley height. So what we did is, as a first step, we just reproduced their relationship or their correlation between valley width and upstream drainage area. We get the 3 different exponents for the 3 different lithological classes. And then we calculate also here the R-square values. So how well does this power law relationship describe actually the data points? And then we actually repeated this regression exercise, but now we normalize the valley width for the valley height before we do this. So here on the y-axis, we have now valley height normalized, valley width normalized by valley height, again plotted against area, and then we just repeat the regression. So what we can see is that in all cases, I mean, there's still a lot of scatter in the data, but in all three cases, our R-square values increase. And yeah, I don't want to say that this is a validation of our model, but what I want to say is that this is like one of the first or simplest tests we could do, and that the model fit actually gets better instead of worse, at least does not falsify our model, I would say. Okay, so to sum up, paired terrace sequences require that valley width reduces with time. And we have observed at these different field sites that this reduction seems to scale linearly with valley height. So in order to actually explain this observation, we're proposing a new model, or an adjusted model. And this model proposes that lateral sediment supply, particularly from river-independent hillslope erosion processes, reaches some kind of balance with the lateral sediment removal by the river. And the nice thing is that this model is actually able to explain how a valley width in climatically formed terraces, how valley width gets reduced in these climatically formed terraces. And with that, I would like to thank you for your attention.
Thanks a lot, Steffi, for this very nice talk. So the chat is open for questions, so please do not hesitate to ask questions directly on the chat. You can also raise your hand to ask for the mic to ask a question. So we already have one question by Matt O'Berry. Couldn't sediment transport across terraces be aeolian rather than fluvial or hill slope, especially in unvegetated valleys?
Okay, so couldn't sediment transport across terraces be aeolian rather than hill slope fluvial processes? So what, I'm not exactly sure I know totally what you mean. So maybe you could specify a little bit what you mean by aeolian transport across terraces. So because we have seen, or we can see these network structures on the terrace surfaces, and I think they form because there's water flowing across, and with the water, sediment is transported. There's probably also sediment transported by wind that might get deposited there, but I think this is not the main mechanism that brings all the sediment down to the river channel. Maybe it helps, but it might not be the main process, in case this is what the question was about. Sorry.
Yeah, I think it was. Thank you, Steffi. So we have another question. So maybe Aditi, if you want to ask it. Or...
Oh yeah, I can do that. There's a question by Monica. Is the size or shape of sediment uniform across all terrace walls? In this photo, it appears that grain size can vary dramatically and could change bed load dynamics significantly.
Yeah, so I can only answer for this one terrace site where I have worked. I haven't been to all the other 11 sites. So this image here, in case you refer to this is not an image from one of the sites. This is just an image that actually shows this process of lateral sediment supply here. But in this terrace sequence in the Toro River, there is some variability, and I also tried to quantify these differences in grain size, which is kind of hard because like you have some parts where it's kind of fine and then it's coarse again. So we have tried to do this, and wherever we did it, we don't see like in general great changes in the D50. So it seems to be overall comparable also when we compare to the modern sediment distribution in the modern river channel.
Thank you, Steffi. So we have another question. So maybe, I don't know if it was Rebecca or Michael that want to ask question. No? Okay, I can go for it. So we have a question by Marcus Fuchs. Thank you, Steffi. Do you think there might be a difference between sparse terrace and accumulated or soft sediment terrace formation?
Yes, this is a good question. And in the very beginning, I was looking at both, but then I thought I'll only use the alluvial terraces because then I don't have to worry so much about differences in rock strength. So I did analyze a few bedrock terraces, but like maybe 3 or 4, and they also seem to show this linear relationship. So I think there is the potential that the same process also plays a role in bedrock terraces. There's also sediment coming in laterally. However, I would guess that the rates are very different. If we are in these alluvial settings, it's a lot easier to actually remove alluvium and also transport it down. I think for bedrock terraces, everything is just a lot slower.
Thanks a lot. I think we had a very similar question by Anne Voigtlander, and I think you already replied to that. So maybe we can switch to a question by Emma. I don't know if you want to ask it.
Yeah, I can do that. Emma says, thanks for the talk. I really like all the photos. I'm wondering about aggradation in the valley from the upstream sediment. Couldn't a lot of aggradation in the valley generally make the valley width height ratios be higher?
Yeah, so that's definitely a point. So if we imagine a setting where the valley actually widens, and then we have a phase of aggradation, so the valley width maybe stays the same, but it actually reduces the height of the terraces. So when we now go and measure, we actually measure a height that is in a way too low for how it has really been. But what we actually think is, so if we have aggradation, we actually reduce the height of the wall. So that means the valley in theory should widen even a bit more. And I think overall this widening phase, it happens in this unconsolidated sediments fairly quickly as well. So that's the idea, right? You very quickly reach some kind of steady state between lateral input and what the river can remove. So what actually happens is if you aggrade again, you reduce the wall, so there's less sediment coming in laterally. So in theory, the valley should widen just a bit more. And we think this is actually what might happen. Like if you have aggradation, it might just adjust by widening a bit more, and then it reaches the new balance again.
Thank you. Another question by Michael Kirkby. Is there a case for paying more attention to channel gradients and sediment load, both quantity and grain size, supplied from upstream?
Yeah, I think so there are studies that look at the role of sediment supply on lateral channel migration. And I think it's quite an important parameter. It definitely plays a role when it comes to the movement of river channels. As far as I know, there's no study that looks at how much sediment is carried by the rivers and how high or how much sediment is coming in laterally, like the ratios. I think that would be very interesting to do. When it comes to channel gradient, I think it's something that has been attracted some attention recently. There's some work that came from Liran Goren's group that was published fairly recently, and they have particularly looked at the role of valley width, not only thinking about discharge and lithology, but also looking at channel gradient. So I can refer to that work.
Okay, thanks, Steffi. There's another question. There's a question by Todd. Hi, Steffi, nice talk. In most of your cartoons of valley profiles, you showed bedrock under the terraces with alluvium on top. And in your field photos, like the last one, we only have thick alluvium, no bedrock visible. Is it possible that the terraces are forming on previously infilled material and that might somehow play a role?
So the cartoons I showed in the beginning, they are a little bit more general. So this is like the general idea of how valleys evolved. And then there's always some kind of bedrock around, even in the alluvial valley. It is only in this last part, in the second part, in our study, that we were only focusing on alluvial valleys. So, okay, I have to quickly read the question again. So is it possible that the terraces are forming on previously infilled material? And this might somehow play a role. So the terraces that I was analyzing were formed on previous infilled material. So there's bedrock somewhere far around, but it is not touched at any time by the river. So I think when it's just all filled with sediments, then the bedrock around doesn't really play a role. But of course, when we have a setting where we have a bedrock valley and just some alluvium at the bottom, then of course it's like the bedrock around that really sets the rate of lateral erosion and valley evolution. Todd, I'm not exactly sure if this answers your question, but I hope it does.
Yeah, let's say it does.
Okay.
So we have another question by Nilesh. Could be the narrowing of the width caused by the increase in incision rate?
Okay, then the question is, of course, like if you just increase incision and stop lateral erosion or reduce lateral erosion, this could potentially narrow the width. But the question is then, what drives this increase in incision rate? I'm sure there are sites where this is the case, like when you have a long-term change in the tectonic setting and you, through time, increase incision rate, then this might cause a narrowing. But I think it's very unlikely that all of these sites that we have analyzed, all paired terraces around the world are simply formed because we have an increase in incision rate. I think it's like a special case that exists, but it doesn't explain all of them.
Okay, thanks, Steffi. So there's, I think, this one last question by Jingtang, who says that it's a very inspiring talk. Do you expect that the equilibrium cross-section of the valley would be totally controlled by the diffusion process, or to say that the final valley slope would be the response angle of the alluvial materials?
Yeah, so I think, I mean, what actually happens is with these upper terrace levels that are not in contact with the river anymore, they will start to diffuse, and they will eventually maybe get to the angle of repose. So I guess this is something that will happen over time, so that the individual terrace rises will actually reach that angle. Yes, I guess that's quite likely.
And actually, I have a question, Steffi. So in the last model you developed, so you are able, by fitting your data with this linear model, to obtain the second term that depends on this hill slope erosion that is independent from the river, if I get it. Can you really pinpoint values of this erosion rate and compare it to the rate of erosion by, let's say, the effect of river on their banks? And does it make sense? Or
so I think what happens, so in a classical case where we don't have terraces, I think both of these processes happen, right? So you have, like, if you have a V-shaped valley, whenever the river incises or it erodes the walls, you kind of oversteepen and the entire wall will adjust. And this is the response simply by lateral river erosion. But in addition, you might also have river independent erosion because you have rainfall and like frost weathering or whatever. And I think both of these processes can play a role at any site, and they may be, like, how important they are might differ through time. It is just at these terrace sites that they offer this kind of unique opportunity that we can separate them, because here only the lower terrace can be eroded by the river, while the upper terraces are basically protected. So they only have this one process happening and not the other one. So regarding the importance, I would say if you imagine a very narrow valley and a river moves laterally, I think it's really the lateral river erosion that dominates, that causes most of the hill slope erosion, most of the lateral sediment supply. But then once you reach these steady state width, then the idea is that the river, so the river moves and it can remove a certain amount of sediment. So it only spends some time at these outer parts of the valley, and it removes just the amount of sediment that comes in from hill slope erosion, basically. So once the valley gets really wide, it's actually the hill slope erosion that dominates, and lateral sediment and river erosion starts to become less important because the river needs all its transport capacity to remove the sediment that comes in from the hill slopes, and it hardly ever touches the walls to really widen them because, yeah, just no more capacity.
Thank you, Steffi. So we still have time maybe for one question if there is someone that is quick to type in the chat.
Can I ask a question here?
Yes, of course.
Thank you. So first of all, it was a great talk, very interesting. Thank you. And what I wanted to ask, if your sites include several pairs of terraces, and the sediments is getting only by hill slope processes, that means that the rate of the hill slope processes is supposed to increase as we get closer to the river, right? Because the upper terrace, the higher terraces, they supply only the sediment from the close hill slope, but the lower terraces will need to transport the sediment from above and the sediment that they produce. Do I understand correctly?
Yeah, okay. So I think like there's two different things. So one is like how much sediment gets transported across these hill slopes, but I mean the terrace rises, so the steep parts, it is pretty steep. So I think the sediment can very quickly go across or go down there. Yeah. So that is like the amount of sediment that gets transported. And you're right in a way to say the further we go down the hill slopes, the more sediment needs to be transported across one point. Like it needs to transport the material that gets produced at the lower slope, plus all the sediment from the upper rises or from the upper slopes. But the idea is that the rate by which each wall, so if you think about each terrace level, so that retreats, like really horizontally retreats, and that this rate of horizontal retreat, that this is more or less constant. So simply from hill slope erosion.
Okay, thank you.
Thank you, Steffi, and thank you, Helanan, for your question. We have another question, by the way, by Jean-Louis Grimaud. Do you think there are ways to quantify the lateral input of sediments from field data?
Yeah.
A related question.
So yeah, I think there's some first attempts. So another study that I haven't shown here that we try to use as another first order test of our data is the work from Valeria Zavala from Chile. And she uses cosmogenic radionuclides from valley hill slope sediments in order to estimate how much, or what is actually the vertical or the lateral erosion component of these hill slopes versus the vertical component. So it's not super easy because when you measure 10 beryllium concentrations on hill slopes, so okay, let's if you imagine we take a look at this image. I need to get my laser pointer back. So what they did is they had slopes that were a bit less steep, and they just collected sediment that has been coming down from these hill slopes, and they kind of took really mixed samples. So they took several samples over a long distance and mixed them all. Now what you measure is like the total lowering rate of the hill slope, but this total lowering rate can be broken down into a vertical component and a horizontal component. So the idea was, if you have an independent way of quantify the vertical component, then you theoretically could get some ideas on wall retreat rates. So that's like one way of quantifying this over long time scales, like millennium scale time scales. If you think about really short time scales, what people have done is using erosion pins. So this particular for bedrock walls, you put like little nails in the walls, and every year or every few months you actually go and you can kind of measure how much does the wall or the rock retreat. So the head of the nail starts to stick out more and more. So this way you get some wall retreat rates on annual timescales basically.
Thanks, Steffi, for that. So I think we have a very last question this time by Trevor Faulkner. Why are the terraces so flat if there is sediment supply from the sides?
So I think they are initially very flat. But through time, they actually start to become less flat. And I'm not sure if I can quickly jump back to one of these images. Let me see. Okay, so this was the image we were looking at before, and you can see that maybe you can see it better down here. So I think initially this layer that kind of sticks out here used to be the flat terrace surface, but then because there's sediment moving down, you actually start to accumulate sediment here. You kind of produce a sedimentary wedge, and here it's quite thick. Up here, this terrace surface is a lot wider, so you can kind of think that that sediment that is deposited from the upper riser here is a bit thicker here. But once you have developed this transport slope, it gets less here. And then like once the slope is there, you can just transport the sediment across. So they look quite flat in the field, but it doesn't need to be much, right? It needs to be maybe 1, 2, 3 degrees in order to transport sediment across. And that's still quite flat.
Yeah, and I guess the connectivity should increase when you go to lower terraces level, because the width of the flat part is
here for sure, yeah. But yeah, I mean, that is our idea at the moment to explain this observation. If anybody else has another idea, I'm happy to discuss alternative explanations, and would be great to actually have a second model, and then we could test models against each other.
Okay, I think we don't have any more questions. So I thank you once again, Steffi, for this very nice talk. There are many people saying thank you to you, and that they appreciated a lot your talks. So thanks a lot. And we'll have another Landscape Live seminar next week by David Montgomery. So please, you are very welcome to join us. And that's all for today. So thanks a lot for attending. Yeah, it was very nice, Steffi. So there's still a few people in the list, but
yeah, no, really, really nice talk. I really enjoyed it.
Thanks for
not really my area, but yeah, it was really interesting to hear, and very well explained actually. So yeah.
Yeah, thanks. So as I said, I try to be a bit more general to kind of have people follow me if I talk about value.
Yeah, no, it was it was very well done. Yeah.
And,
yeah,
and
nice.
I was wondering, Steffi, for another mechanism, because I mean, you are always eroding into some sediments, and could there be a link to the height of the base level? For instance, I mean, when you start eroding, you will be, if we imagine that we have a constant base level, when you start eroding these sediment deposits, you will be further away from this base level, so you can expect a higher erosion rate and maybe some higher slopes. And when you start developing lower terraces level, you start decreasing, I mean, the incision rate due to coming closer and closer to this base level. Because I was wondering, so in the model you developed, there is a kind of causal link between the fact that the height, I mean, the lateral, I mean, at least in the first model, the lateral height of the terraces are going to constrain the capacity to erode laterally. But if you have a process that control the quantity of incision you do in between each terrace level, then you might have a natural feedback. And if this is related, for instance, to a kind of constant base level that you reach progressively when you incise all these terrace level, I was wondering if it was a possible mechanism or if it's completely stupid. Because I don't know the settings at all. So
So you mean kind of that through time, your overall net incision rate decreases? Is that what you're trying to say? Because you're kind of getting closer to the new base level.
Yeah, and if I get it correctly, I mean, when you go to lower level terraces, the height of these terraces seems to decrease as well.
So I think it depends. I mean, in this particular case that I've shown in Toro, it does, but it's not necessarily the case. There's also terraces where the lower terraces was higher than one of the upper ones. So yeah. So, and I think, I mean, base level changes, they must happen, right? And I think overall there must be some background uplift. Otherwise, you don't have net incision, and you need this net incision. Otherwise, you would just fill up the same space with sediment again.
Exactly.
But I think the special case about these terraces is that the higher levels, they don't feel the base level anymore, right? So it's only the lower terrace that needs to adjust its slope to the base level. All the others are kind of, they can do whatever they want. They don't care about the base level anymore. So I think you can have settings where the overall incision rate would increase with each incision step because you'll get closer to your long-term steady state. But I guess what would happen is if you actually start to reduce incision rates, you actually would start to widen even more. And in these cases, you would probably end up actually destroying your terrace records.
Except if you say that you have a rate of lateral erosion.
That kind of, yeah. So I mean, the question is always then, do you start to change your transport capacities? So if, I mean, the idea that we had is because in these terraces in Toro, they really formed due to this climate cycle. So we thought like at each point along the cycle, the conditions are probably very similar. But if you have like long-term changes in any of these boundary parameters in tectonics, or if you would be in a set